Good morning and welcome to live from Long Island, New York. So today we're going to add something to the osmosis problems, which I know are difficult enough. And actually, in some cases, this makes it easier. This thing called water potential, which we're about to learn. But it's sometimes hurts like the previous process that you learned, and I have some security alert. Who cares? All right. So we're going to talk about something called water potential today. Okay. And water potential is really only applies to plant cells, and not to animal cells. And it's a calculation that you can do, that takes into account applied pressure to a system, that where water is moving, as opposed to just the molarity. So when we were doing previous problems, there was no applied pressure to the system. We were just looking at molarities of the solute and if where the water was going to flow based on where there was the most solute. This is going to be quantified mathematically, and water, as we're going to see, always moves from an area of high water potential to an area of low water potential. And let me get my pen out so I can annotate the screen a little bit. Pointer out to the pen. So again, if a cell has a high water potential, it's likely that the water is going to move out of the cell, because water always moves from an area of high water potential to an area of low water potential. Okay, so this is the formula. Okay, and this is the Greek letter psi. So we had the Greek letter chi, and now we have the Greek letter psi. And this is water potential, as you can see here. And then psi s is the solute potential. And as you add more solute, or more stuff as we've been calling it, the solute potential gets more negative. And again, this will make more sense as we go on and as we do problems on Tuesday. Also in the formula is pressure potential. And we're going to talk about how pressure is created in a second. But there can be pressure on a solution or in a cell, and it can be positive pressure or it can be negative pressure. If it's a pushing force, pushing outward, the pressure is positive. If it's a pulling force, or the pressure is like imploding inward, the pressure potential is a negative number. So if it's pushing outward, it's a positive number. If pulling inward, it's a negative number. And we're going to see this is important in plant cells, which I'm going to show you on the next slide. But one thing that's important to know is if you have a container of pure water or distilled water, the water potential, by definition, is zero, because it has no solute and no pressure. So if you have distilled water in an open container, the water potential is zero. So this we're going to see, this water potential formula that we're going to use, which looks more complicated than it actually is, and we're going to do a lab, I believe, on Thursday, on water potential, is important in plant cells. Because when water moves in and out of plant cells, because of the vacuole, it creates pressure, the large vacuole. So when water moves out of the vacuole, remember that vacuole collapses if it moves out too quickly, and that creates a negative pressure or a suction force, which affects how the water is going to move. If water moves, I should say in, I can't, moves into the plant cell, that's me copying and pasting, so that should say in. If water moves into the plant cell, that it fills the vacuole blows up, and the vacuole puts pressure against the cell wall, and that creates positive pressure. And we're going to see, in plant cells in particular, the water potential formula is better at predicting how water is going to move, as opposed to just using molarities. So here we have an example. And again, there's no writing on this slide, but I want you to sort of annotate as I talk, and explain what's going to happen in this slide. So here we have distilled water, and here we see it has a pressure potential of 0, and my pen went away again, so let me get my pen back. I don't know why it went away. Pointer options, pen. Alright, so it's distilled water, so it's pure water. There's no pressure on it. and there is a solute potential of 0 because it's pure water. So then if you add them together, because water potential is the pressure potential plus the solute potential, that gives you water potential. So the water potential of distilled water is 0. And this is a cell, okay? And this cell is just, just hanging out before this is before it's put in the distilled water, and it has 0 pressure on it. It's a flaccid cell. It's just sort of hanging out. But it has a solute potential of -2, and that's created by the stuff that's inside the cell. And what we're going to do is we're going to put the cell in distilled water, okay? And we're going to see what happens. So what happens when you put the plant cell in distilled water is this has a water potential of 0, and 0 is a higher number than -2. So what's going to happen is water is going to flow into the cell, because remember, water has to flow from high water potential to low water potential, okay? But it's going to do, what is it going to stop? Like, how does it know when to stop flowing into the cell? Well, if you see here, the water flows in, okay, so we're putting the cell in here and the water's flowing in, okay, because this has a water potential of 0, the distilled water, and the cell has a water potential of -2, and we see that it's going to flow in, and what's going to start happening is the vacuole is going to fill up, and it's going to create a positive pressure, okay, which is going to cancel out the negative solute potential. And that positive pressure, again, you want to be writing this down, is created by the vacuole filling up and putting pressure on the cell wall. And the water is going to flow in until that positive pressure created is at a value of +2. So that it cancels out the negative solute potential. The solute potential is always negative if there's stuff in there. And then now the water potential of the cell is 0. Because the pressure created by the water flowing in cancels out the solute potential. And I know this is a little bit confusing, but again, we want to get down to basics right now, and then we'll look more into this in class on Tuesday. But again, the point is that by the water flowing in, it creates a positive pressure force, the vacuole on the cell wall, and that cancels out the negative solute potential, making the total water potential 0. And now it's equal to the water potential of the distilled water. So movement will stop, or it will be at equilibrium. Movement won't stop. It will be at equilibrium, and water will flow in and out at the same rate. And let me just go back for a second to summarize. Being annoying. It won't let me go back. Hold on. And this is what's going to happen if any plant cell is put in distilled water. Water will flow in to the cell until there's enough pressure created that it cancels out the negative solute potential. Alright, so here is an example of a U-tube, okay? And U-tubes help us explain water potential. This is a semi-permeable membrane, so we have pure water on this side, distilled water, and a solution of 1 molarity on this side, but there's no pressure on it. And we can see here that the water potential of pure water is 0. And then the solution on this side, there's no pressure on it, there's no external pressure. But because there's solute in it, it has a negative solute potential, which makes the total water potential negative 0.23. And the units that we measure water potential in are MPa. Don't worry about the units, just memorize them. So we can see in this case, water always has to move from an area of high water potential to an area of low water potential. And this is where the negative numbers get confusing. 0 is a bigger number than negative 2.3, so the water is going to flow in this direction through this membrane. This is assuming that the salt or whatever this solution is can't pass through the membrane as well. Now, what if we wanted to force it to equilibrium so the water couldn't move? Again, this is the same situation, but in this case, we're applying a positive pressure to the system. Okay, that positive pressure, if exactly 0.23, cancels out the negative solute potential. So now the water potential on this side is 0, And now instead of the water only moving in this direction, it's at equilibrium. Okay? Because again, the pressure brings the water potential back up to 0. If we push even harder, more positively down here, now the pressure potential has increased even more. And normally, if we were only considering solute potential and there was no pressure, the water would always flow this way. But if we put enough pressure, okay, we can force the water in the opposite direction. Because now, remember, water always has to flow from an area of high water potential to an area of low water potential. So here, now the water potential is 0.07. That's a bigger number than 0. So even though there's more solute here, the water, because of the pressure, is going to flow in this direction. I'm going to skip this slide for now, because I want to get to the sort of point of this. And we'll come back to this slide in class. So you have one less slide. Alright, so we need to be able to calculate solute potential. Okay, and there's this crazy formula, which doesn't look that crazy. But I'm going to actually move into OneNote so that we can look at the formula and I can write better. And let me move it into writing mode. So, again, we have pressure potential, which we're going to discuss more, again, all more about this formula on Tuesday. But solute potential is a formula, okay? And this is on your formula sheet, so you don't need to memorize it. And the formula is solute potential is equal to negative I, and I is the number of particles the molecule will break up into. If it's an ionic compound, okay, so you're given the formula, it's the number of atoms, so there were 2 atoms here, so it would be 2. For things that are covalent, which are usually they're going to give you sucrose and glucose, the I is 1. And then C is the molarity, that little M thing that we've been doing with. R is a constant, which in AP chemistry was the ideal gas constant. It has a different value here, but it's from that it's the same R, just in different units. And this number always stays the same. It's a constant. It's 0.0831, and it's on your formula sheet. And then we have the temperature, okay? And the temperature has to be converted to Kelvin. So they're always going to give you the Celsius temperature usually. And to convert any temperature to Kelvin, you add 273. So if the Celsius temperature was 22, you would just add 273 to it. So we're going to do this example right here. And again, this is not going to make complete sense, I promise, but we're getting you started. So it says the molar concentration of a sugar solution in an open beaker, so that means there's no pressure on the system, is 0.3. Calculate the water potential at 27 degrees Celsius. Round your answer to the nearest hundredths. So we first, remember, water potential is equal to the solute potential plus the pressure potential. Here the pressure potential is 0 because it's in an open container. So we have to calculate our Ys. So our Ys is negative I. And here this is a covalent compound because they don't give us a formula. If it was salt, NaCl would be 2, but because it's a covalent compound, the I is 1. It only breaks up into 1. It doesn't get pulled apart. The sugar molecules don't get pulled apart. They just get separated. Again, that's chemistry. You don't really need to understand that. C is our concentration. So again, we're using this formula here, down here. And they told us that was 0.3. Our R value, right here, 0.0831. And then we need to calculate, change this to Kelvin. So 273 plus 27 plus 273 is 300. And then you put this all into your handy dandy calculator and multiply them all together, and you get negative 74.79. And remember, the units are megapascals. And since the pressure potential is 0, that goes in there, and that's actually this is also the water potential. We're going to see that any number that goes in here makes the water potential more negative. So whenever you add solute to the system, the water potential gets more negative. And remember, water has to move from an area of high water potential to an area of low water potential, so that has consequences. So again, this wasn't made to make complete sense. It was kind of just to introduce you to the concept of water potential. We're going to do some problems and look at it more closely on Tuesday. Have a good weekend.